This is the 4th lecture, and as I had promised, this would be a problem session, the first problem session on DC analysis of BJT circuits. Before we take this, take the problems, let me mention two things that I have discovered. Another book which is available in the library, and it's a good book comparable to Burns and Bond and what is the other, Millman and Grable. This is Cedra and Smith. This is called Principles of Microelectronic Circuits, or simply Microelectronic Circuits, I think. You have to consult various books, there is no other way. The material is so large and so technology oriented, things are changing so fast, books become obsolete in a very short time. The other thing that I wanted to mention is that in FET, in the discussion on FET, this will require in solving one problem. Our relation is ID equal to IDSS. Oh, that's why I must put on my specs. IDSS 1 minus VGS by VP. This was the relationship, okay, squared, provided VDS is greater than VGS minus VP. Okay, if this happens, then we are in the saturation region. We are in this region, okay, in the saturation region. This is the relationship, okay, between current and the controlling voltage VGS. The relationship is not linear. This was the story for JFET, junction field effect transistor. Well, the story is quite similar with the MOS transistor also, and I just want to mention this relationship before I go to solve the problems. In the junction field and the MOS FET, for some reason the relationship is written as sum K multiplied by VGS minus VT whole squared. If you compare this with this relation, you see this relation can also be written as VP minus VGS whole squared, and VP squared can be brought out and combined with IDSS, alright, and since we are squaring it, it does not matter whether you take VGS minus VP or VP minus VGS, alright. So the relationship is exactly the same, except that for historical reasons, for JFET it is written like this, for MOS FET it is written like this. Instead of VP it is VT, because I will explain this in a moment. Obviously the this is in amperes or milliamperes, let us say usually it is in milliamperes. The constant K, the dimension shall obviously be milliamperes per volt squared, that is right, per volt square. And when there is a problem on MOS FET, usually the value of K shall be given. If it is JFET, the value of IDSS, that is the drain current under saturation conditions for VGS equal to 0, shall be given. Now the other thing that I want to mention is that in MOS FET, you know, there are two types, enhancement mode and depletion mode. For enhancement mode, VT has the interpretation of a threshold voltage. Threshold voltage. This threshold is for saturation again. Okay, this threshold is for saturation. That is, beyond this, the collector, the drain current gets saturated. On the other hand, in the depletion mode, once again the pinch off phenomenon, the same phenomenon, and therefore there VT is the same as the pinch off voltage. Nevertheless, the relationship is very similar for both JFET and MOS-FET. MOS-FET, whether it is enhancement or depletion, only thing that changes is the interpretation of this constant. It is either a pinch off voltage or a threshold voltage. And to denote that this is MOS, even if it is depletion mode, we use the symbol VT. Is that clear? Okay. So this is all that I wanted to tell you about MOS-FET. Now let's take some problems. The problems have already been given to you in the tutorial sheet, and I had asked Mr. Joshi to work out some of the marked problems. Some of the tougher ones I left for the problem session. The first problem is that you have a transistor like this. It's drawn a bit unconventionally. The battery is like this. This is the emitter, this is the collector, this is the base. So it's an NPN transistor. The arrow goes out, but it's a common base transistor. Okay, this is RC, R sub C, and this is VCC, and this current is IE. This current is I sub C, and the conditions of the problem are that VBE is given as 0.65 volt, alpha is given as 0.99, I sub CO is given as 10 nanoamperes, which means 10 to the minus 8 amperes. Okay. VEE, that is this battery, is 5 volt. VCC, this battery, is 10 volt, and this resistance RE is given as 500 ohms. Okay. Then you are required to investigate this circuit under two conditions. That is, essentially what you have to find out is the operating point. That is, the things to be found out are I sub C and VCE under two conditions. One is R sub C equal to 1K, and the second is R sub C equal to 2K.
Excuse me, sir.
Yes.
Given to find out VCB.
Okay, VCB, that is this voltage, right? All right, VCB. Now let's look at the solution. Is the problem clear?
Yes.
These are the parameters given. You are required to find out the operating point IC and VCB under two conditions, RC equal to 1K and RC equal to 2K. You will see that the operation differs drastically. Let us see what happens. First, you notice that I sub E, this current, you know this voltage and you know this drop, VBE, this is 0.65, and therefore I sub E is VEE minus, okay, this is VEE minus this drop, I am sorry, I must show it here. This voltage from here to here is 5 volt, and from here to here is 0.65, and therefore very simple application of Ohm's law gives you I sub E, this divided by RE. And if you substitute the values, 5 minus 0.65 divided by 500 ohm, so many amperes, and this comes out as 8.7 milliamperes. I have worked them out, so I'll skip the numerical. If I made a mistake, point this out to me on a later occasion. My numerical calculations I am not very confident about. Okay. Now the transistor, I don't know whether the transistor is in the active mode or saturation mode. I don't yet know. So in these problems, one does not proceed blindly. One assumes a mode. Let us assume an active mode. If there is a contradiction, then we shall investigate the other mode. Okay. So let's assume that the transistor is in the active mode. It is also suggested by the fact that this voltage is 0.65. However, there is nothing sacred about it, because as you know there is a small variation from transistor to transistor. So let us assume an active mode. Assume active mode. If that is so, then I sub C, the collector current, would be alpha I sub E plus ICO. Okay, and you see that alpha is 0.99, this is given. I sub E is 8.7 milliamps plus ICO is 10 to the minus 8 amps, and therefore we can safely ignore this. We can safely ignore this compared to the other one, and this comes out, my calculation is that it is 8.61 milliamps. Okay. Then under this condition we have found out I sub C. The other thing to be found out is VCB, and as you see VCB is nothing but VCC minus IC RC. So VCB VCB is equal to VCC minus I sub C R sub C, and this is, what was VCC? 10 minus 8.61 milliampere multiplied by R sub C is given as 1K. R sub C is given as 1K, and this comes out as 1.39 volt, which means that the collector base junction is indeed reverse biased. Okay. VCB is 1.39 volt, collector is positive with respect to the base negative, and therefore our initial assumption of active region is justified. Okay. Now let us see what happens when RC is changed to 2K. If the same conditions are valid, alright, then our VCB should be equal to 10 minus 8.61 milliampere multiplied by 2K, which becomes minus 7.2 volt, which indicates that the transistor is no longer in the active region. It is forward biased, and if it is forward biased, then it cannot exceed 0.7 approximately. Okay. If it is forward biased, VCB we are talking of, not VCE. VCE is approximately 0.2, VCB is actually the junction voltage. So if it is forward biased, let us assume that it is equal to 0.7 volt. Therefore VCB is equal to minus or plus? Minus 0.7. Your conclusion at this point, as soon as you find out VCB is negative, you should say therefore Q must be in saturation. Okay, Q must be in saturation. All right, let me write it down. Q must be, Q is the transistor. We don't use capital T. Why not? T is used for absolute temperature. But then Q is also used for something else, but traditionally this is gone in. So VCB is minus 0.7. If that is so, then I sub C, this is an assumption. You could assume 0.8 or 0.6 also, because it varies from transistor to transistor. Then I sub C shall be, this is interesting. Let us go back to the circuit. How is VCB 0.7 volt? Okay. We have found out that VCB, if we assume an active model, then VCB comes out as minus 7.2. Now a diode, a forward bias junction diode, cannot drop more than 0.7. That is why we said 0.7. Okay. Now what was the other point? Oh, how do we find out now I sub C? You see, VCB is minus 0.7, and therefore it adds to VCC. Yes.
So does the relation VCE equals VCB plus VBE hold?
It has to. KVL. KVL cannot be violated.
So, but in this case, VC is approximately 0.2 volts.
Correct? So VC, VBE also
VBE
changes.
is 0.65.
VBE cannot remain 0.65 anymore because it's in saturation. It will change. Agreed? It will not remain 0.65. It will change. But that is not a condition of the problem. We don't require to take care of it. If we have to take care, then we have to find out. If we assume VCB is minus 0.7, VCE is plus 0.2, then the resulting voltage will be VBE. VBE will change. The point clear? Now, how do I find I sub C? This voltage is 10 volt and there is a positive to negative, no, I'm sorry, negative to positive, and therefore I sub C would be 10 minus VCB, which is minus 0.7. Is the point clear?
Yes.
Okay, that divided by 2K. RC has changed to 2K. So this comes out as 5.3 milliampere. Alright, this is the condition, this is the solution to the problem for part B. Any question?
Yes, sir. How can you take VCB as only 0.7? If it is an active saturation region, it should be 0.75.
Okay, we took a good figure 0.7. You can take 0.75. It's not specified and therefore, but it has to be in that region, 0.5, 0.6 to 0.8. This is the region. You can assume any value. Any other questions?
So, but under normal thumb rule condition, we take VBE and the saturated to be about 0.75
Correct.
and the VCE as 0.22.
That's right.
But in such a case, VCB becomes 0.55, minus 0.55.
Okay.
So 0.7, isn't it a bit larger than what it?
Take minus 0.55. It's just an arbitrary figure in that range. If it is specified, then you have to use that value. Because, for example, VBE is 0.65 specified, this is for the active region. We have to take that, we have no choice. But if it is not specified, assume any value that you like. You cannot assume VCB equal to minus 70 volt, for example. It has to be within this small range, 0.5 to 0.8. Okay. Any other question?
So as you were saying, if it's 0.55 volts VBE, then we know that for a diode to be forward biased, the voltage should be about 0.6.
This is what I am saying, about. So it can come down also. From diode to diode they vary. This is the rule of thumb. This rule of thumb is VBE sat is 0.8, VBE active is 0.7 and VBE cut in is 0.5. This is the rule of thumb. If nothing else is specified, these are the values that you take. Okay? Now, was question 3 done in the class? No. Tutorial class for the 2 classes that were held? No. So we'll take problem 3. In problem 3, we have a 5 volt source, a 1K resistance, a transistor Q, NPN transistor, and there is a resistance of 47K here which connects to the base. This is a silicon transistor with beta as equal to 100. You are required to find out whether Q is active, saturated or cut off. And you are required to find out I sub C, no, I sub C is here, I sub C and VCE. Okay. I sub C has to be found out and VCE has to be found out. Beta equal to 100 is given. Alright. Here also we will assume a condition. Now, can the transistor be cut off? Is that a possibility? Cut off is a possibility? No, because I sub B is not 0. If you see there is a 5 volt source connected to, this is 1K, there is a 47K, so there will be some base current and therefore the transistor cannot be cut off. So it's either in active or in saturated mode. Let's assume that it is active. Let's assume that it is active. assume active. Then in the active region, I sub C would be equal to beta times I sub B, that is 100 I sub B. Let me draw the circuit. This is 1K 5 volt and this is 47K. This is I sub C is 100 beta, 100 beta times IB, 100 IB, and this is IB, I'm sorry, in the other direction, IB. Okay, so if I write KVL around this loop, then obviously 5 would be equal to 5 volt would be equal to, what is the current through 1K? 101 IB, that's right, 101 IB multiplied by 1K, alright, plus the drop in 47K is IB times 47K plus the drop from base to emitter, we assume it to be, since we assumed active, we assume it to be 0.7, from which you can find out IB.
Excuse me, sir.
Yeah.
Sir, how do you take voltage to become 101 IB?
Because I assumed it active. What is your question? How do I take,
Sir, 5 is equal to 101 IB, how?
101 IB. This is this is 100 IB collector current and this is IB. So 101 IB. Okay. What was your question? 0.7 because we assumed active. Alright. From which I get IB, my calculation gives me 29 microampere. So I sub C is equal to 100 times this, which is 2.9 milliampere. If that is so, then VCE would be VCE would be 5 minus 101 multiplied by 29 microampere. Agreed? And this comes out as 2.071 volt. Okay, right. Which means that our initial assumption was valid. That is
Into 1K also, 101 into 29 microamperes into 1.
absolutely, absolutely correct. It must be multiplied by 1K. This is the drop. So therefore, our initial assumption that Q is active, it is true. It is active. And we have also found out I sub C and VCE. Next question, we are going from tougher to tougher now. 4, 5 has been done. Now we go to question number 6. Any question on this? Question 6, you must pay your complete attention. Yes.
What is the minimum DC voltage for assuming that the transistor
If it is in the region of 0.2, then it is saturated. And also, you know the test for saturation, I sub C by I sub B must be less than B. Okay, so there are a couple of checking points. Alright, question 6 concerns this problem, this circuit. If you look at this circuit, I have drawn it separately because I shall need a number of them. I have drawn it separately. There are two transistors, let me describe. There are two transistors Q1 and Q2, both are silicon, and it is given that beta for both of them is 100. It is given that VBE sat is equal to 0.8 volt. VBE cut in is 0.5 as we have been assuming, and VBE active is 0.7 volt. There are two transistors Q1 and Q2 and the collector of Q1 feeds the base of Q2, all right, and then both the emitters are brought to a common point VE and connected to ground through a 1K resistance. This is the circuit. And I have shown in the brown color the various currents. This current is IC2, this current obviously is IC1 plus IB2, simple application of KCL. If this current is IB1, then obviously the emitter current would be IC1 plus IB1, and this current would be IC1 plus IB1 plus IC2 plus IB2. Agree? Okay. Now, so the question is understood. Not the question, the circuit is understood. Let's look at the question. Question says, if V in, first part, if V in is 0, that is this input is 0. 0 means it is not left floating, it is connected to ground. Okay. If V in equal to 0, if V in is 0, then Q1 obviously shall be cut off. There is no base current. So V in equal to 0 means Q1 is off. Instead of cut off, I write simply off. The question is, what is the status of Q2? Is it active or saturated? Q2 active or saturated? Let's solve this part, then we shall go to the other parts. And under this condition, whatever Q2 is, find out V0 and VE. These are the two things to be found out. Now, we have to make whether it is active or saturated, we have to make an assumption, all right. And as you will see, we usually make there is a guideline for making this assumption. You don't proceed blindly. You see, if Q1 is off, no current flows through IC1, obviously IB2 will be large. Isn't that right? Because all the current that comes from here, this is going to go off here, and therefore there is a possibility that Q2 may be saturated. So we assume that Q2 is saturated. Yes.
So in this case, the circuit that we are dealing with is similar to the circuit that we did in the previous question.
No, it is not.
Q1 is off.
If Q1 is off, it is very no. There is a
Resistance.
this resistance that creates a difference. So assume Q2 to be saturated. If Q2 is saturated, then it's the same circuit, okay? IB1 is 0, this is 0, therefore IC1 is 0, right? Therefore it is only IB2 which comes like this. This is totally 0, okay? So 5 minus, this is the 5 volt, I want to find out what is IB2 first. What is IB2? IB2 is 5 minus, if Q2 is saturated, this voltage is 0.8, 5 minus 0.8 minus VE, whatever that voltage is, okay, minus VE divided by 10K. Is that correct? Yes. I have found out IB2. IB2 is 5 minus 0.8 minus VE divided by 10K. All right. Then next I want to find out IC2, this current. IC2 would be 5 minus this voltage, which is 0.2 minus VE divided by 1K. All right. And you notice that the sum of these two currents, IB2 and IC2, will now flow through 1K, and that will cause the drop VE. So I sum up these two, 5 minus 0.8 minus VE divided by 10K plus 5 minus 0.2 minus VE divided by 1K these two currents, this should be equal to VE divided by 1K. Agree? The sum of these two currents, IB2 and IC2, should be equal to the current through 1K, in which only VE is unknown, and therefore we know VE. VE comes out as 2.49 volt. Okay, and if I know VE, then I can find out now IB2, right? If I know VE and I substitute here, I found out IB2. Is the point clear?
Yes, sir.
Yes, sir.
This is 171 microampere. It works out to, if I substitute this here. On the other hand, IC2, if I substitute again here, IC2 comes out as 2.31 milliampere. Agreed? So now my test for saturation. What I do is IC2 by IB2 is equal to 2.31 milliamps divided by 0.171 milliamps, 171 microampere. So this is less than 100. Obviously, if it was 100, the numerator would have been 171. Therefore, Q2 is indeed saturated. And if Q2 is saturated, then what is V0? V0 is this voltage. V0 is from here to ground. So it will be 0.2 plus VE. How much did you find out VE? 2.49. So this is equal to 2.69 volt. And the problem is solved. Okay? First part problem. If I want to have your complete mind in this, because I am going to do some interesting plots now. If I plot V0 versus Vin, Vin equal to 0 leads to V0 equal to 2.69 volt. Let's say somewhere here, 2.69 volt. All right? Obviously, if I want to change this state, if I want to make Q1 conducting, then I have to increase Vin. Let's do that. Let's do that. So the part B of the problem says, if Vin is increased, instead of 0, instead of connecting to ground, you connect a source, voltage source there, to a value of VE in part A, this voltage, what was this? 2.49 volt, plus how much do I need for conduction of Q1? 0.5, cutting. So VBE1 cutting, that means equal to 2.99 volt. So if Vn is increased gradually to 2.99 volt, then Q1 will start conducting. And it says, show that Q1 not only will start conducting, it will saturate. Show that Q1 will saturate and Q2 will be off. And under this condition, you have to find out Vin. We have already found out. Find Vin and resulting V0. All right. This is what we have to find out. So assume that it is so. Is the problem clear? In the previous case, in the case A, V in was 0. Now you are taking V in lead out of ground and connect it to a voltage source and increase the voltage. Obviously Q1 cannot conduct till the voltage VBE1 reaches cut-in, which means that V in has to be the cut-in voltage plus whatever VE was. During this process of increasing V in, VE remains the same because Q1 remains cut off. As soon as it starts conducting, it takes no time to go into saturation. Let us see whether it goes or not. So assume that this is true. If there is a contradiction, then we will say sorry, Q1 is not saturated. Okay. So assume that this is true, and if this is true, then obviously V0, if Q1 is off, I'm sorry, if Q1 is saturated and Q2 is off, then assume this. If we assume this, then what is V0? 5 volt. Because Q2 off means there is no IC2. Agreed? Now what else do you have to find out? You have to find out under this condition what is VE? I must take another page. Okay. If Q1 is saturated and Q2 is off, V in was made 2.99 volt to make Q1 conduct. But when it is saturated, what is V in? When Q1 is saturated, what is V in? V in would be VBE1 saturated, which is 0.8 plus VE. So the new VE, it is previously VE was 2.99 volt, I'm sorry, 2.49 volt, and then you added a 0.5 to it so as to make Q1 conduct and Q2 is put off. Now when Q1 is saturated, its VBE increases from 0.5 to 0.8, and therefore VE shall also change. Therefore VE becomes 2.99 minus 0.8, which means 2.19 volt. Is the point clear? No. Okay. You see, as soon as Q1 starts conducting, in no time it goes into saturation. VE cannot change instantaneously, so it remains at 2.99. If it does so, what changes is the voltage across the base emitter of Q1. It changes from 0.5 to 0.8. Therefore VE shall now change to 2.19, because the input remains the same. Input remains at 2.99. Alright, so this is 0.8 and therefore this becomes 2.19. If it does become 2.19, then what is the current? I must go back to this figure. You see, this is off, this is 0, and this current would be IC1 plus IB1, and VE is 2.19. Therefore IC1 plus IB1 equal to 2.19 volt divided by 1K, which is 2.19 milliamperes. I can also find out IC1. I can also find out IC1 as 5 minus 0.2 minus 2.19. Okay, 5 minus 0.2 minus 2.19 divided by 10K, and this works out 0.261 milliampere. Then what is IB1? This minus this. Okay, IB1 plus IC1 is 2.19 milliampere, and IC1 is this. Therefore, IB1 becomes 1.931 milliampere. Is there a doubt that the transistor is saturated? IC1 by IB1 is a fraction now, much less than 100, and therefore indeed Q1 is saturated. It takes a little time, it doesn't occur instantaneously because there is space charge which has to be cleared. If Q2 is saturated, there is charge accumulation which has to be cleared, and that charge has to come and dump on Q1 to make this saturated. It does take a little time, but for such calculations we don't take care of this. We will take care of this in digital electronics. What time does it take to switch states? Now you see, if I go back to my figure, I do have this, okay. 2.69, then V in was 0. Part B says if I increase V in to how much? 2.99, then what does V0 become? V0 becomes 5 volts. So it immediately rises and becomes 5 volt. Okay? 5 volt, and it remains 5 volt. If you increase V in beyond this, because Q1 is saturated, there is no change. Alright? The output remains at 5 volt. Now suppose you want to go back to the original state. That is, if you want to go back to the original state, then what do you have to do? You have to decrease V in till Q1 comes to the which region? It was saturated, so first it would come to the active region. Alright, this is what part C of the problem says. Now let me look at part C. Part C of the problem state. Now to switch back to the original state, V in must be reduced until Q1 is active. Reduce V in until Q1 is active. That means this voltage reduces to 0.7 volt. VBE1 reduces to 0.7. Yeah.
Now we've been told that while increasing V in, we never reached the active state. While
Yes, we did. From cutoff, it has gone via the active state, but it has reached the saturation very quickly. So quick that in the oscilloscope you won't be able to see the vertical part.
and would we be able to see that when we bring it down? V in?
Well, you see what happens. See what happens. It has to come through the active region. So from 0.8 it cannot suddenly go to 0.5, it must, or 0.2, it must go through 0.7. Okay. Now, so intermediate state is active. V must be reduced until Q1 is active. If Q1 becomes active, then VBE1 would be equal to 0.7. And if I want to change states, you see Q2 was off earlier. If I want to make Q2 conducting, then this voltage VBE2 must be reduced to 0.5. Okay. Now what is VBE2? It is also VCE1. Isn't that right?
No.
So, yes?
Yes.
This is the collector, this is the emitter.
Yes.
So VBE2 is the same as VCE1. Therefore, what you do is you reduce V in such that VCE2 becomes 0.5 and immediately Q2 will start conducting. Alright? You are required to find out what is this V in. V in to be reduced to what value such that this happens.
That both are in active region.
They will not remain so. They will not remain so, as you will see. We will see this. Okay. So, if I apply KVL and this transistor has just started conducting, then obviously No, I'm sorry. We go to KVL via this. Okay. Then therefore 5 volts shall be equal to what will be this current? This will be 101 IB1. All right. This current IC1 plus IB2. No, I'm sorry. Hold it. Cut-in means what? The Q2 has just started conducting, which means the current IB2 has just started flowing. So you take that current as 0. Then IC1 would be simply 100 times IB1. So it will be 100 times IB1 multiplied by 10K. This is the drop here. Plus cut-in voltage is 0.5 plus VE. What would be VE now? This current has just started flowing. It is still 0. So VE would be IC1 plus IB1. That means 101 IB1 multiplied by 1K. Alright? Is the point clear?
Yes.
V in is now reduced until Q2 just starts conducting. When it just starts conducting, IC2 is 0, IB2 is 0, but a little increase will make both of them non-zero. So my KVL says 5 volt must be equal to the drop across 10K plus the cut-in voltage plus VE, and VE is the 1K drop due to current IC1 plus IB1. Now what does this give you? This gives you IB1, and IB1 comes out as 4.1 microampere. So what is V in then? What is the value of V in? V in is Q1 VBE1, which is in the active region, so it is 0.7 plus this voltage VE, which is equal to 101 times 4.1 microampere multiplied by 1K. Therefore, this V in is surprisingly 1.11 volt. This is not 0. Now if you go back to this diagram, you see V in at 2.99, it had changed state from Q1 off to Q2 off. When you reduce from 2.99, you have to come up to 1.11 to make it change state. That means Q1 goes to active region and Q2 goes into conduction. Now, this state does not remain so. Ultimately what happens is Q1 becomes off and Q2 gets saturated. That is, it comes back to this state. Alright. So if I show the direction in which I went, I increased. Initially the power supply was put on, Q1 was off, Q2 was saturated, and this is the condition. Then I increased V in. How did I reach this condition? Initially the base of Q1 was connected to ground, 0 voltage. Then I connected a battery and continued increasing. If I increase up to 2.99, then suddenly there is a change of state, and this state remains like this. If I want to come back, then I reduce V in, and I have to reduce up to 1.11 to be able to change again to the other state. Okay, this is a highly nonlinear circuit, and this circuit is called the so-called Schmitt trigger.
So why this abrupt change at 2.99 volt?
Why this abrupt change at 2.99? At 2.99,
Gradually increase from 2.69 to 5 over a period of Vn.
Actually there will be a small slope here, as I said, because the current takes some time to build up. But it is so fast that you won't be able to see it in the scope. In the scope you will see something like this, a rectangle.
So won't there be a region where Q1 is active but Q2 is still cut off?
It is a very transient region. It is not observable on the scope. It's almost vertical. The time taken, it can be analyzed. It can be analyzed. It will be done in the digital electronics, yes.
So in Q2 you took IB2 as 0.
In Q2, I took IB2 as 0. That's right.
So in that case IC2 also will be 0.
That's right.
So in that case IE2 also will be 0.
IE2 will also be 0.
So VE should be 5 volts.
No. Why should V be 5 volt? VO is 5 volt. Okay. Any other questions? This is one of the experiments that we will perform in the lab class.
So in part B we get the condition that VE is 2.19 volts.
Right.
Right, sir? So if we reduce the VN to 2.19 volts, then VBE goes below 0.5 volts.
I cannot reduce that. You see, all control that I have no control over VE. All control that I have is in VN.
Yes, sir, right.
Correct.
So, but in B case, we are at 2.19 volts VE.
Correct.
If we start reducing it to 2.19 volts.
Reducing VN.
VN to 2.19 volts.
Okay.
So then VBE becomes less than 0.5, obviously.
No, it doesn't happen because in the meanwhile, Q2 changes its state. It doesn't happen. You see, all these phenomenon, if you do it gradually, you will see that suddenly in the oscilloscope, if you are observing the output as long as it is steady, it will be a straight line. Suddenly you see the straight line jumps up, and suddenly the straight line jumps down. Okay, you will actually see this diagram in the laboratory. This is a Schmidt-Krieger circuit, and one of the experiments in the laboratory is this. We are about at the end of the time. What about the other two problems, 7 and 8? 7 has been done. So question 8, I will simply tell you what the problem is and then I will give you the solution. Question 8 is, there is a 5 volt source, 1K, there is a 10K here, and there is a diode here, a very special diode called the Schottky diode. And the Schottky diode, SHOTTKY, Schottky diode has a drop of 0.4 volt. Unlike the ordinary diodes, which have an active in the active region cut-in 0.5, saturation 0.8, and so on and so forth. Schottky diode is approximately 0.4 volt, and this is connected to the base. This is I sub B, and this is I sub C. You are required to calculate, this is I sub D. You are required to calculate IC, ID, and IB, and you are also required to answer whether Q is active or saturated. Well, the solution methodology is the same, that is, you either assume it to be active or saturated. I assumed it to be active. If there is a contradiction, it will come out. I assumed to be active, and I found out, I will only give you my results. It's nothing but you apply a KVL. That's about all that you. All circuit problems require an application of KVL and KCL and at the most Ohm's law. Nothing else. These are the three equipment that an electrical engineer has to solve almost any problem. Okay. My solutions are I sub C. No, I was too lazy. I didn't put them in the calculator. It is 5.13 milliamps, which is approximately 5.13. 100 by 101. I sub B is equal to 5.13 divided by 101 milliampere. I assumed it to be active, so it has to be this. And I sub D is equal to 0.43 minus 5.13 divided by 101. That is, I calculated the current through this and subtracted ID. So many milliamps. These are the solutions. And since these equations are consistent, our initial assumption that the transistor is in active region is justified. If this was not consistent, then you would have recalculated. Alright? Our next tutorial and next problem session will be on FET, DC analysis of FET circuits.
Rolling is the process of producing different components by plastic deformation of work material by passing it between rotating rolls. The process is called longitudinal rolling if the forming rolls are rotating in the opposite directions and flow of work material is along the length of the job and perpendicular to the central line of the rolls. By this process, we can produce products like bars of different cross sections, steel for constructional work. Flat products like plates and sheets of various thickness can also be produced by this process. Another version or type of rolling process is transverse rolling. Let us have a look at a transverse cold rolling machine. In this process, the forming rolls are rotating in the same direction and the flow of material is either radial or the flow of material is along the axis of the job, which is also parallel to the axis of the forming rolls. A large variety of products like pulleys of different sections, rollers for overhead cranes, cycle freewheel,